Okay, so to start with, let me summarize what we have done in the last lecture. We have started with a probability overview, but the two important things in probability we need to know is conditional probability, which says the probability of A given B. How do we define it in this way? And accordingly, we define chain rule and all. And the most important rule of today's lecture, as well as in this learning, is the Bayes rule, where we could define the the conditional probability in a flipped way. So to know A given B, the probability of that, if we know that B, what is B given A, we can also estimate that based on prior and a marginal knowledge. And we see that all these probability notions sums up into a table which we call as joint probability distribution table. If we have the knowledge of the full set of distribution and their probability in the joint distribution table, we can arbitrarily know anything about the probabilistic nature of any event and their composition. So just by summing of the rows, in case of conditional probability, just by taking a ratio of the summed over rows and something. So this is what we need in the probability overview counterpart. Then we revisited our learning problem, which tries to hypothesize an unknown function. Only it knows a training set of examples, that is a set of attributes leading to a classification value of y. It can view only that and can find out the unknown function. We have seen that for concept learning and decision tree learning. However, we change our premise a little bit by saying that why not we also try to find out what is the probability of y. Let's say it's a classification problem. Then what is the probability of y being positive and what is the probability of y being negative, discrete values of y classes given the attributes. So such kind of a learning we call as Bayesian learning, where we try to use the Bayes rule or kind of conditional probability by seeing that given a new set of attributes, which class is more probable, then I will classify it to that class. However, to our utter surprise, we say that joint probability distribution is very good, but we cannot use it in practice due to data sparsity. So we have to think about smart probability estimations. So one of the smart probability estimations that we devise from our common knowledge of coin flipping, if we have a large set of data in our hand, then we will try to see that how that data, how can I how can I make my estimation more accurate towards the data. So I need to choose my estimated probability such that it maximizes the probability of that choice given, for the data that is given based on that choice that I make. So that will follow my data. And theoretically, we write it this way. And in coin flip example, we have seen that our common sense or basic intuition matches with what we want to make as a likelihood estimation. We stopped here, but we also had a note in the last class that we made another type of estimation where our data is not that much strong or there are less amount of data in our hand. So we cannot try to estimate as we do in maximum likelihood. That is, estimation will not follow the data because data may carry now or misinformation due to very less amount of availability. So for that, we started to think about maximum a posteriori analysis, and which I will start in greater details today. So as you know that maximum a posteriori analysis, what we want to do, we want to maximize my theta. Sorry, we want to choose a theta that maximizes probability of theta given data. You want to choose a theta that maximizes probability of theta given data, which means that in mathematical sense, my map estimate that I will come up with is, if I write it mathematically, it is simple that I want this to happen. However, in Bayes rule, if you allow Bayes rule here, what you want to happen is now you can see that this factor is what we do is this one is our likelihood. I mean, how do we interpret this one? This one is our prior knowledge. So I know that since I am trying to estimate, so some prior knowledge about the distribution of this theta I need to know, that we call as a prior. And this in probability term, we call it as a marginal. However, to get a argmax of that, you can easily understand that the numerator is only dependent on theta, the denominator is not. So therefore, our only concern will be to get a maximum out of the numerator part. That is this part only. Now, remember, since I have less amount of data, so this prior plays a very pivotal role here. So you need to know some information about the prior knowledge of your estimation. So if you take the example of coin flip once again, if you try to remember that we had an algorithm to find this, and we say that the estimate that we give about heads and tails is nothing but some number of pre-computed heads divided by alpha 1 plus some number of pre-computed heads plus alpha 0 plus some number of pre-computed tails. Why I did that? Because this acts as a prior to me, because my prior knowledge says this pre-computed head over pre-computed head plus tails are the prior knowledge about the coin biasness. Because if you do not have any data, that is your alpha 1 flips of head is 0 and also alpha 0 flips of head are 0, then your prior knowledge dominates whatever be your estimate. Now gradually, if you have more and more data, let's say alpha 1 you have 1000 and alpha 0 you have 1000 kind of a thing, or maybe 1 lakh kind of data. Therefore your alpha 1 component dominates and your prior cancels out. So that's why this is an online learning algorithm. By intuition, we thought out that we will go on flipping and try to estimate using this rule. Now, exactly this will come if we can leverage our prior to in suitable manner by maximizing this as per our equations that I will show today, and just back it up our estimation by statistics. So let us assume that as you know already from the maximum likelihood, that we have this as, let us assume the prior as a beta distribution. And why I take it, I mean, at the end of the lecture, I will try to tell you the beta distribution, why I take it this way. So it says that suppose my prior knowledge follows a distribution of coin flipping, which is a beta distribution. So this is, let's say this is of the form like this. So it's a binomial distribution, but we call it as a beta distribution. We call it as a beta distribution of theta given this. We write it in short this way. So if I know that my prior coin flipping falls into such kind of a distribution, and this is my maximum likelihood thing, then again what I am trying to do is, just wait a minute. Yeah, then again what I am trying to do is I am trying to maximize this into this, because the numerator term only I need to maximize. So I am trying to maximize, let's say this is alpha h and alpha t2.
Hello, sir.
Yes.
Sir, beta distribution is problem dependent or it is universal? That means for all we use the beta distribution.
No, not for all. I am using it for my coin. You can use any distribution as your prior, but that prior means that you know a little bit about the domain. So I am assuming by coin flip domain, I know that coin flip distribution a little bit will follow this.
Okay, sir. Okay, sir.
And since it's a binary flipping, so I can use beta. Otherwise, I will use Dirichlet distribution. I will show it in a minute.
Okay, sir.
There are many distributions you can assume, but you need to assume something, right, of the prior. Otherwise, how can you estimate?
Sir, excuse me, sir. Prior means you are telling that we have some kind of knowledge that the coin, the distribution of heads and tails would follow this kind of thing.
Yeah, this kind of thing, but you do not know the exact bias. So you are assuming that such kind of a distribution may follow as a prior.
Okay.
So see, what the prior will do, the prior will dominate these things, right? So now if your data are more and you have a wrong estimation of your prior, then automatically it will cancel out.
Okay, sir.
Right? If my data is more, I am not prioritizing my prior value. But if my data is less, I need to do something, right? So my prior then will dominate.
Okay.
So that's why if you try to do it this way, you see this is the just like earlier equation. What we will do, we will take a, so instead of taking argmax of this, what I will do is that I can take a log of this and do the same thing. So when you do this, as per my previous lecture, if you assume, then the theta map will exactly come what in the earlier lecture it was alpha 1 and this was alpha 2. So it was coming alpha 1 divided by alpha 1 plus alpha 2. So this will come alpha h plus beta h minus 1 divided by alpha h plus beta h minus 1 plus alpha t plus beta t minus 1. Now what does it signify? You see, it signifies the exact intuition that we have in our coin flip example. So the white box that I am bracketing is our hallucinated pre-thought about the distribution prior. So therefore,
Okay,
you can easily understand that our online algorithm in both the cases, in MLE and MAP estimates, if we do not have much data or if we have ample number of data, so this MAP estimate is a good estimate because if you have more data, you can follow this one will dominate your prior knowledge and automatically data will be more likely. If you have less data, then your prior knowledge has to dominate because unless you have something, you do not learn. I mean, you do not estimate anything. So that's why if we take beta distribution, you can see that our common sense falling up. And why I take beta distribution, there is something in statistics which is called conjugate prior, where your final answer is of the same data type, is of the same structural type as your prior. Then we call it as a conjugate prior. You see, this likelihood and this is of same type. Also, when you multiply it and try to find your final probability of theta given data is of same type because it is coming of the same type, style of expression. So we call it in common sense, we call it as a conjugate prior in statistics. And usually when people try to estimate such kind of a thing, you see, this is my prior. I will try to figure out some prior which resembles my likelihood data. That's why I took this kind of a beta prior in two-part classification, that is heads or tails. And if you try to look around in a more generic sense, we will use. So let me write the generic sense. This is maximum likelihood. So in maximum likelihood, what we will use if there are, let's say, instead of a coin flip, if we have a 6-sided die to flip in. So there will be multiple outcomes instead of just heads and tails. So I have multiple outcomes I will try to do. I will try to do theta 1 to the power alpha 1, theta 2 to the power alpha 2, and so on up to theta k to the power alpha k, where my
question.
Yeah.
So why did you represent the probability of that of theta given data as a beta distribution? Like, how can you justify that?
No, I do not want to justify it. I am saying that if I have a distribution like this, I will get my map like this, which resembles the common sense fact that I need to have some prior knowledge which I could add up to this. You change your distribution, you will get a different estimate. I have no objection of changing this one. This will be domain dependent and example dependent where you want to make your learning happen, estimates happen.
Hello, sir.
Yes.
Sir,
I didn't complete the answering of a question. Please try to understand. Let the person says yes or done, then you pitch in. Yeah. So did I answer your question?
So I'm a little confused. Sorry if it is. Just
See, what is p theta according to you? It's a prior knowledge.
Yes, sir.
Why do we need that? Because as per our common sense, our prior knowledge should dominate where there is very less data.
Yeah.
That you understand. So whatever you take as a distribution, I do not care. But what I want to say is that since in the coin flip, there is a prior knowledge and we are doing it. See, we have a thought process of flipping the coin, heads and tails occurring. That's why I took this beta distribution as my prior, because it should resemble my coin flipping thoughts, like something is head by theta and something is tail by 1 minus theta.
Okay,
So,
sir, I understood now.
yeah, that's
Yes.
why I took a prior which relates to my distribution and knowledge. If it is not the case, you can take any arbitrary distribution. Something you will resemble, but the format will be just like your intuition. That's what my point is.
I understood, sir. Thank you.
Yeah. Next question. Whoever I just stopped him in between.
Hello, sir. Sir, for less amount of data, we are using the MAP. And for that, we are also using the prior knowledge. But in that case, in prior knowledge also, we have less amount of data. Then how to get the distribution?
That doesn't make any, doesn't come into any sense. See, prior knowledge is a distribution. It is not related to a less amount of data. It says that if it could be like this. So see, let's say, what about why you estimate your coin flipping like this? Prior knowledge of pre-heads and pre-tails. So maybe your coin flipping, it's an online algorithm. So the more you get the data, the better you will be. As I said, machine learning, if you do not have data, you have no chance of approximating anything. The less amount of data you have, the more domain knowledge you have, you will get more closer. The less amount of data you have, if you have a less domain knowledge, you will be absurd. Your learning will be bad. That's what I can say. See, there is a balance. Either you have a big data or you have a certain domain knowledge to play around with the small data factor. So when you are doing it online mode, so you are taking one by one data. So as your data set grows, your estimation becomes more accurate. Theoretically, later we will prove all this. But
okay, sir.
If your data set is also less, your prior is also haywire. I mean, you take something weird kind of a prior that doesn't make sense at all, then your learning algorithm will be bad. That's what. Okay. So if we generalize it, as I was saying, it's just if I try to generalize it in terms of k classifier, I mean, instead of heads and tails, if I have a k number of answers, so we take the prior as a what we call as a Dirichlet prior, and as you can easily understand, what we do is we just like the previous
Hello,
one.
sir.
Yes.
Sir, I have a question on the previous slide. Can you go over there?
Yes.
Actually, sir, so which equation you have differentiated, like the probability of probability of theta given data, right? So what is the probability of p data over here, where it is like marginal that you
P data is not required because I am trying to maximize where my theta are only in the numerator. There is not in the denominator. It's a constant term. So in differentiation, it doesn't matter.
Okay, sir, got
Sir, I have one question.
Yes.
Sir, prior knowledge, that is, so there is a different process to find that, like beta distribution for coin flipping. So in different domain, that should be a different formula, right?
Yes. The prior knowledge should be a different for different domains, definitely.
Proven already reduced distribution, right? If I
I
don't know
couldn't
distribution
get.
of any domain, I cannot find out ML.
If you do not know distribution of any domain, it is risky to use MAP estimates. In that domain, if you do not know data, do not take that project of learning.
But is there any way to get the prior, I mean, the distribution before I?
No, that's what I am saying. I'm saying that see, prior knowledge is our hint. If you do not know how to solve a problem, if you are not given with the examples to train for that, if you not know that what will be the answer to the problem or how to solve it, do not touch that problem. That's my suggestion. See, learning, you need to have data or some prior estimates to approximate well. You can learn, but you will be shooting more I mean, your tolerance will be much lesser, right? If you have better prior estimations or if you have more data, you are likely to give better estimates. That you can understand, right?
Right.
So in scenarios where you cannot find any prior knowledge, then if you do not have data, if you have no prior knowledge but have data, go for MLE, as you can understand. But if you do not have any data as well as not prior information, I mean, learning, you still can do learning, but your learning has a risk factor of not approximating things well.
Okay.
So here we get it as a Dirichlet distribution, which we just write it this way. It is the same thing, and we call it as a Dirichlet distribution of theta with beta 1 up to beta k. And then also, if you try to make the map estimate with this prior knowledge, you will get the same thing. This will be alpha 1 plus, or rather I will say that alpha k, not k, alpha I plus beta I minus 1. So this is theta map of ith, let's say in a dice, the ith number occurs. That probability will be this way, and this will be for all, let's say j equal to 1 to k, you have alpha j plus beta j minus 1. Just like the two flipping case, we just declare here like this way, this plus this. If it is a multi-valued attribute, then the estimation will come this way. There is nothing much to think on this, because it's just a different distribution, because I now have different classification classes rather than only two. So the main point is that, I mean, what we want to summarize is joint distribution table has the demerit of data sparsity. And as the name data sparsity says, you can understand that data sparsity means that you have less amount of data for all possible columns. Now, if you have sufficient represented data, you go for MLE, where you have data representation sufficient. May not be all, as in joint distribution table, you have all 2 to the power n entries, but there are sufficient representation. Where you have less amount of data, but you have a prior knowledge, but less data, you go for map estimates, which says maximum a posteriori. So the name comes from, you have a prior knowledge and you are predicting a posterior knowledge based on the Bayes rule. That's what the smart estimation things means. I mean, you have to be either smarter in estimating from less amount of data with a prior knowledge, or have to be smarter from estimating whatever data you are given, not even if not it is full. So these are some of the ingredients that we need to know for our learning algorithm, because I can now again pose the same question of learning. So till this point, if you have any questions, you can ask, then I will move next.
Sir, I want to confirm something.
Mm-hmm.
Sir, in the map case, we are using probability of theta given data because we have some prior knowledge, so that we can get that p theta probability in that multiplication of the numerator, right?
Yes.
Yeah. Okay.
So just we are using the Bayes rule in this step, nothing else. So we are using the Bayes rule. That's why we need a p theta thing, which we call as a prior.
Okay.
Sir, if I do have prior knowledge and if
Yes.
I have enough data, still I can use MAP, right?
Both. If you have enough data, you can use both. See what will happen. See, your MAP will give you this, right?
Yes.
If you have a huge data, so your alpha 1 will be much higher than, it will dominate your prior knowledge. If alpha 1 tends to infinity, alpha 0 tends to infinity, then prehistory of heads and tails doesn't matter. It will be just, if you have large amount of data, it will be just like this. So your MLE and MAP will converge to the same place.
Got it.
Yeah. Good. Now again, coming back to our classical question that we have a joint distribution table and all that, we know conditional probability. So now coming back to our learning question, let's say we are classifying with a set of n attributes. So this is what we want to answer now. So as you can see that if you have a joint distribution table, it's pretty bad because you need to have 2 to the power n rows if there are n attributes. For example, in this case, what we are trying to learn is probability of wealth given the gender and given the hours of working. This is what we are trying to learn. So if we have the full distribution table, we need to estimate 2 to the power n minus 1 number of cases, because one case we can eliminate, it is sum 1 minus the whole sum. So why n? Because I have n number of attributes. This is 1 and this is 2. So hence the total in the joint distribution table. I mean, I am saying that this is n plus 1 number of, let's say, a the space. So in the total distribution table, it is 2 to the power n minus 1 or 2 to the power n 8 estimation I am needing due to this 3 values. I mean, all of this plus y. This includes 3. Now, if you go by, so it will be better if I write it 2 to the power n plus 1 minus 1, because I am assuming 2 attributes. Now, if I go by this way, that let's say I compute probability of reach given the gender and hours worked. So I only need this because, so I only need 2 square number of estimations to make. This is nothing but a conjugate of this, because this plus this equal to 1, as I have considering 2 classes, rich and poor. I hope you understand, because probability of poor given gender and hours work will be just 1 minus of this. So this is redundant. If I know this, I can also know this class. So for each of the combinations or each of the values, since it says it takes gender takes 2 values and hours worked is thresholded by 40.5, it can take 2 values. So I am getting this many number of computations. So therefore, if there are n attributes, so the number of estimates that I require, you can easily see, is 2 to the power n. Agreed? Just by computing it here. So by estimate, I am not confining to only MLE or MAP. I am saying any kind of estimates, if you want to make it from n attributes, you need to compute these many, at least 2 to the power n number of entries to find out a classified value of y.
And so what was the 2 power n plus 1 minus 1?
Oh, I was just telling the length of the joint distribution table. So these are all, if joint distribution table is given, you do not have to do any estimates. But still, the number of probabilities that you need to know is 2 to the power n plus 1 minus 1. If there are n attributes, right?
N attributes. Sir, in this case, the attributes are hours worked and
gender. Both.
Gender.
2. So 2 to the power 3 minus 1, 7 you need to know. The last one is 1 minus of the sum of the others. That's why I said 2 to the power n plus 1 minus 1.
Okay.
Okay. But see, the problem that we started off with, we will not get this joint distribution table is not visible to us. This is not for us. For us, we need to estimate such kind of a thing, and estimation can be done by MLE or MAP. But my question is that if you need to determine the value, classified probability value, let's say y equal to 0, this given these attributes, you need 2 to the power n estimates to confirm, because each estimate will give such kind of an answer. So there should be 2 to the power n estimates. So if I get a new, if I get a new attribute of a problem, if I know this 2 to the power n estimates, then I can classify it whether it is y equal to 0 or y equal to 1, which probability is more. See, I am moving towards the learning problem. What I am saying is, what I need to know to classify y equal to 0 given a new set of attributes. So this is our learning problem. To know this, What you need to know, you had to know this 2 to the power n estimates. Now see, these are not, forget about the joint distribution table, just forget about this. I am saying these are estimates because you may, for many large set of attributes, you may not have all informations, but your MLE or MAP estimates can give you these values. Now, how many estimates do you need to judge any new attribute falling into y equal to 0 or 1 category? You need to know 2 to the power n estimates. Yes or no?
Yes, sir.
Yes.
Good. Let me move on. So we have learned Bayes rule. So let's say if Bayes rule can help, let us see if my y, let's say y equal to 0 or 1, anything. One, I am doing 2 class, so one estimate is okay. So therefore, this, given the Bayes rule, gives me this. So if I want to find out the class of given these attributes, how many estimates I have to make here? If instead of this formula, I have used Bayes rule and used this formula, it didn't help because I need to have all the estimates for this plus all the estimates for this. Also, I need to have the estimates for probability of y and probability of x1 up to xn, because these two doesn't sum up to 1. If you have something here equal to 0 and 1, they sum up to 1. But given that something 0 and 1 doesn't sum up to 1, you can see that given that something 0 and given that something 1 doesn't sum up to 1. And therefore, for this, I need 2 to the power n minus 1 estimates. For, let's say, for this, I need 2 to the power n minus 1 estimates. Even if I pre-compute this for this, let's say 1 estimate. So effectively, I am needing 2 into 2 to the power 1 minus 1 plus 1, even if thinking that this is pre-computed, all the compositions. So it is not, it is even worse than this one. So directly applying Bayes rule doesn't help. Are you getting the problem? See, my problem is that I do not have joint distribution. This is my number one problem. I have a subset of the data. I mean, a very low subset of the data. As you can see, if I have 100 attributes, and most of the columns in the joint distribution tables are unknown. So with that, what I can do, I can use MLE estimates or MAP estimates depending on my data and prior knowledge availability, but I can come up with these classes for the given data. I can come up with these values for the given data. So if I need to compute all such, directly I am computing it in 2 to the power n steps. If I use Bayes rule, it doesn't help because it is doing worse. Now, for a new thing to classify, what I will do, for a new thing to classify, I will just try to ensure what is the probability of this being 1 or what is the probability of this being 0. And whichever is the highest, I classify it accordingly. That is my goal. Now, to classify something new, I will say this is my training phase. So my training phase needs 2 to the power n estimates at least in the way we are doing. So 2 to the power n estimates is huge because for 100, it's a huge, and we usually do with 50,000, 1 lakh, even 1 crore features. So you can see that if each estimate takes a fraction of a second even, then all these estimates computing to find out the classification boundary is impossible. Right? Can you sense the problem right now?
Yes, sir.
Yes, sir.
Good. What can we do about this? The next question. So the question in our hand, we want to classify by having training with this data. We want to classify a new thing. What can we do? how can we train it instead of training for 2 to the power n estimate ways, or calculating 2 to the power n estimates during training. So let me again go back to statistics and try to find out our fundamental concepts. In statistics, there is a concept called conditional independence. One of your friends just had a prior knowledge, so he peeps up this thing. I say that X is a random variable, is conditionally independent of Y given Z if, so I say X conditionally independent of Y given Z if I can write this thing, that probability of X, Y, Z is equal to probability of X given Z. So you see that this is a definition of conditional independence in statistics, that I say X is conditionally independent with Y given Z if this thing happens. That is, probability of X given YZ is the same as the probability of X given Z. Example, you know that lightning, when you see a lightning, immediately a thunder will come. So raining doesn't have any conditional dependence with the thunder coming if there is a lightning. So therefore, probability of thunder given the rain and lightning is equal to probability of thunder given lightning, because whenever lightning happens, thunder will automatically come, whether it is raining or not, doesn't matter, given you see a lightning happen. Remember, this is very interesting, that given this thing, otherwise it may not be conditionally independent. So this, with this definition, what does it help? Let us try to see mathematically. So we are trying to invoke this training by using Bayesian rule. Sorry, this is one thing I missed it here. Now, what does this term is now saying? If I can say that, if I can make an assumption about the conditional independence of each of my attributes. So the way that I choose my attributes during a classification problem, if I can choose it in a conditionally independent way, how does it help? So let us try to see for two attributes, x1, x2 given y. So what does this mean, x1, x2 given y? How can you say? Chain rule, apply chain rule. x1 given x2y into probability of x2 given y. The first one, since x1 and x2, I assume that my attributes are conditionally independent. So therefore, in general, you can write it as a multiplication of, if your x1, x2, x3 all are conditionally independent, if these things are conditionally independent. But in terms of learning, what does this assumption bring? This assumption bring to a fact. See, when you assume something in your learning framework, you only generalize your learning, right? Maybe some bad examples also come in, maybe some good examples also come in. You do not know whether this assumption of making conditional independence will affect your learning or will help your learning. So therefore, now your only goal is that whichever learning problem you are given to solve, you try to figure its attributes so that it becomes conditionally independent with each other. Then it is a very good problem for Bayesian example, because now my estimation of y given x1 to xn attributes boils down to the fact that I have x1 to xn given y into probability of y by probability of x1 to xn, which is basically applying the conditional independence. It becomes probability of y into right? Because this term, by the conditional independence assumption, has reduced to this term. Now, how many probability estimates you need for this? N for y equal to 0 and n for y equal to 1. So you can see that you need 2n and y, this number of estimates for during training to figure out anything during after you train and then try to classify. Is this part clear, that where we are trying to make an influence into?
Sir, please repeat this this calculation, that 2n plus 1, just two steps that you did.
Yeah, 2n plus 1 comes from, see how many probability values you need to estimate. Here you need to estimate n probability values given y equal to 0, also n probability values given y equal to 1. Here one probability value more. Here is one more, but I am assuming that suppose this is given to you as your previous thing. So amount of this estimations you need to make more.
Okay, sir. Okay, got it.
So, I mean, let me summarize the whole thing. We started off trying to find out, without any joint distribution table, we are trying to figure out how can we train from the attributes this value. So to train it, we see that we at least need this many number of rows in estimation. So we need to estimate either using MLE or MAP at least 2 to the power n. There, if I apply Bayes rule, it doesn't help, it becomes worse. But indeed, Bayes rule has a fact to play if we try to see that if we can pitch in our conditional independent notion. It's an assumption, first of all, conditional independent. It is very difficult to find all attributes that are not conditionally dependent. But assume a scenario that if you have found it, then your computation of estimates will be significantly lesser. So with n equal to 10 to the power 6, 2 to the power n is totally meaningless, whereas 2 into 10 to the power 6 plus 1 is very admissible in the number of computations. So you have a meaningful algorithm, computational algorithm to estimate or to train a Bayes classifier.
So,
yes.
The above formula you have written, like probability of x1, x2 given y, will also have probability of y, right?
This one.
Yeah, yeah.
Oh yes, no. See, I am writing it the chain rule factor here. Oh, so yeah. I missed it. Yeah, I missed it.
Yeah. Okay, sir. That's why this probability of y came in the last, right?
Yes.
Yeah.
Yes.
Sir, it should be 2n plus 2, no? Because
yeah. I mean, I mean, see, I am only bothered about this order.
Yes, sir.
I am saying that I make it into order of n from exponential.
Okay, sir.
I mean, you just the estimates is more dominated by that term.
Okay.
So now see, your training is that given the partial set of joint distribution table, you use MLE estimates. For example, let us only concentrate on MLE and suppose think that you are given a table with sufficient data, may not be the full exponential set of data, sufficient amount of data. You train it and build a classifier. Giving a new example, you try to see what that classifier results. If your probability of y equal to 1 is more than half, you classify it as a positive. If your probability of y equal to 1 is less than half, then you classify it as negative. This algorithm, we call it Naive-Bayes algorithm. And believe me, though it's an assumption of the conditional independence of selection of attributes, it works like magic in your spam filtering, in your news article separation in your text classification. But see, I mean, it works like magic, though. See, in spam filtering, what we do, suppose you get such kind of a message. I have a message for you to look into. See, this is a spam, as you can easily see, because there are something you get, right. I mean, I'm just looking it in a more sense. You see, this kind of a thing is a spam, right? I am someone who is someone, some heart condition is well, give me some money, or you get some certain amount of amount in our bank. There is no one to invest. So what are my attributes here? My attributes here are number of these words occurring here. So the words that are occurring here will act as an attribute to me. And in English, it has been seen there are 50,000 words that we colloquially use to communicate. So at max, there will be 50,000 attributes. Traditionally, in general English communication, we do not use more than 50,000 words. But see, now 50,000 attributes, if you go by your generic principle, you get 2 to the power 50,000 number of probability estimates you require. Whereas here 2 into 50,000 number of estimates you require. And so just let me finish up with this algorithm. So what we are trying to do in the naive-Bayes classification is, let's say if, for example, this is spam or not spam, it's a binary classification. But news separation is not a binary classification, because it could be a sports news, it could be a financial news, it could be a political news. So therefore, I say that there are there are n number of classes that you want to classify, and given there are k classes, they've given the value of the class is yk, and I try to make it like this way, that given that the attributes that you choose, if you write it using Bayes rule with the conditional independence assumption, what I did in the denominator, I just expanded it. You remember, right? When you have PB in the denominator, so PB, you can expand it as PB given. So if you write it PB and A bar plus PB and A, and then you can easily write it as P A bar into P A bar plus PB given A into PA. So in this way, I just, for each of these values, I just expanded this summation, nothing else I have done. So here, your naive-Bayes classifier, as you can see that your naive-Bayes classifier will just take on each of the training examples. So suppose what it will do, suppose you have this table. Let's say I have 3-element table, and this is my classifier answer. So let's say in my first element table is that the subject ML is good, the subject ML is boring, the subject ML is bad. Here in this, say that I study this attribute takes 3 value. I study regularly, or I study occasionally. And suppose this has 2 attributes, that I perform well in the in the examination of ML, I do not perform well, I perform bad in the examination. And this says that whether I remember ML after this course is over, or I do not remember ML. So with this attribute set, you are given, suppose this set of data. Let's say good R B is your minus. Similarly, good O B is your minus. Let's say some bad but I read and I remember, let's say plus. So this is, let's say, boat. This is, let's say, bad. And I O, and then B, let's say plus. Then let's say G, R, W, say plus. So these are your data given to you. See, this is not a full table. Suppose only this much is your training example. So what you need to do? MLE estimates, because Bayes algorithm is based on MLE estimates. You need to first find out probability of this and find out probability of this. What is the probability of plus? Probability of plus is only these examples are available. MLE estimates, alpha 1 divided by alpha 1 plus alpha 0. Then what you will do? You will try to estimate what if x1 is good given that it is plus. What is x1 is good given that it is minus? What is x1 is bore given that it is plus? You are getting, right? These estimates, all these estimates I need to make in now. Yes or no?
Yes, sir.
Yes, sir.
So what will be this probability? How do you compute only from the table? So you see which entries are good with plus along all the plus entries, because it's a conditional probability. So it will be 1/3, because these three are plus, among them this is only good. So this probability will be 1/3. So in this way you compute all of them, assuming that whether the subject is good, whether I read it or not, whether I remember. Usually these three, I am assuming that these three are conditionally independent variables. So when you get all these informations, that is your training. Now what will happen? Suppose you get out of the box one example. Suppose you get B, O, W. This is your X new in your hand. How do you classify? What will be your Y? What you will do? For this example, you will again try to resort to this kind of probability estimates, and taking the values from here, you can determine the value of Y. Let me come in a new slide, or maybe erase a little bit of thing so that I make it some space here that will be easy to understand. Suppose this is a new attribute that is being given to you, where you say that the three attributes are B, O, W. That I am getting bored. So this is bored. This is O. I occasionally read, but I still remember the concept after the class is over. So then I want to see what will be my class Y equal to plus, given that board plus O plus W is my attribute set. So this is again using Bayes rule. You can see that this is nothing into probability of O given Y equal to plus into probability of W given Y equal to plus divided by this sum. Just do the sum for all. Probability of Y equal to plus into this plus all possible combinations. So you know each of the ingredients now, because that is through estimation learning you have done. You fill up here, get a value of Y. If that Y equal to plus this probability is more than half, you classify this point as this, otherwise not. Clear?
Yes, sir.
Anyone has any doubt? Because this is the Naive-Bayes algorithm. In textbook you will find, very cryptic algorithmic description, but this is it. What we do?
Sir, I understood, but could you just repeat it once in a very concise manner so I can just
okay.
Understood.
Concise point number 1, we will use MLE for estimation during training. We have data. I will estimate every possible parameters through MLE in the data. Probability of Y equal to plus, that is how many plus out of how many data I have. Probability of Xi equal to G given that Y equal to plus. So these many sets says me Y equal to plus. In that given set, G is only 1, so probability is 1/3. In this way, I will estimate everything. single attribute given y equal to plus and given y equal to minus. That's my training done. Getting a new attribute, I need to classify now. With that training data where I have these all informations of minuscule probability values, I just take that computation once again with this new attribute. And if the computation results probability of y equal to plus is higher than probability of y equal to minus, I will classify this attribute as positive, otherwise negative.
Okay.
That's
Understood.
it. You take this example, compute in your home, you take this example, compute all the probabilities, right? Take a new example, classify.
Sir, excuse me. Sir, we are using MLE for estimating the probability y equal to yk. Sir, is there anywhere we are using MAP as such in this algorithm?
I mean, 12 p.m., 12 noon today. Just hold your breath for tomorrow morning.
Okay.
I will show you the problem.
Okay, sir.
Why we cannot use always MLE. Okay. So to summarize, since it's almost 12 p.m., just let me summarize what we have started off with. So with the MLE MAP estimates, now our job is to learn first of all. So when we started our learning, we say that if joint distribution table is not available to us, it will be the case because we do not know everything. So we need to use the estimates that we just learned, MLE or MAP, to the power n number of times to have a meaningful answer to our classification solution. However, we have seen that Bayes rule directly it is not well enough because it makes us more. So the earlier one is good, but it is not good because 2 to the power n is exponential. So we thought about something called conditional independence formula. And if we can select attributes which are conditionally independent, then the estimates come down. But what are the estimates? Estimates are these granular values. Now naive Bayes just exploits those. So naive Bayes rule, given a data, let's say we are using MLE. Just from this, we are trying to say what is the probability of x2 is r given y equal to minus. What is the probability of x2 is r given y equal to plus? All these things it computes. Okay. Then what will happen in such a case, if it computes this way, then my training is just the estimations. That's my training. New classification, I will again follow this conditionally independent Bayes improvisation and try to see what my class is. Whichever class probability is higher, that will be my class. And that is all, be all and end all of naive Bayes algorithm. So in tomorrow's class, I will just dig down the questions that you raised. I will show the pitfalls of such kind of an analysis. And therefore, your MAP estimates will come into place, number one. Number two is that always we have thought that these attributes are discrete. So I will move to continuous attributes. And number three, what I will try to show you is that in every learning algorithm, ultimately there is a decision boundary, right? In decision tree, it is easily visualized that something is plus here, something is minus here. I cut it off into places. Here, it's a probabilistic sense. Somewhere your probability goes more than half, you goes to that boundary. Or maybe if there are multiple classes, the most probable class you put that into. So how does the boundary look like in visualization? That's something you may think of over the shower. How does the boundaries look like? I mean, it's in the hyperspace. Okay, that is good thing to ponder. We will resume tomorrow with all these questions. Any questions on this?
Sir, I have a question.
Yes.
Sir, with respect to the conditional independence, totally conditional independent event, is it possible to do in practical application? Because
it is
conditional
not
total
possible. No, I understand. See, it is not possible. But see, why these algorithms are being popular in machine learning? There is nothing deterministic solution you can give. So the conditional independence is an assumption over the environment, and the more you bring in assumptions in your algorithm, the more generalized you do, or maybe more specialized thing you do. But in case of such kind of problems, spam filtering, your Gmail automatically sends your mail into spam folder. How does it do it? Because it has certain kind of words which are attributes. Its occurrences are the probabilities, and based on that, it uses just naive Bayes. You search, it uses naive Bayes, and it classifies. It's a spam one.
I got it.
Similarly, same thing happens when nowadays you see Google, suddenly in Gmail you type and send something if there is no attachment, but you have written some word attached or something, it is here,
Something missing
it is,
attachment.
right? Here it is, but don't attach. You will see it will give a flag that you have not attached. Why? How does it give it? I mean, it says millions of mails. It watches millions of mails, computes this MLE kind of estimates the training, and then gives a go at it with a conditional independence assumption. But see, I mean, there are many more variations. I am stating the first cut algorithm. If there are a little bit dependent, what will happen? All these ramifications I will discuss, but the algorithm improvisations I will not discuss in the scope of this course. But what will happen if they are not independent? Tomorrow's class I will discuss.
Yes, sir. Yes, sir. Thank you, sir.
Anything else?
Thank you, sir.
Okay, let us stop the recording.